Ladies and gentlemen, welcome to the T-Systems webinar, Teleoperated Driving, New Possibilities with 5G Connectivity. My name is Alexander Heintzel, Editor-in-Chief of ATZ, MTZ, ATZelektronik, as well as ATZ Heavy Duty, and I will guide you through this webinar today. You can expect 3 exciting presentations around the topic of 5G, and we kindly welcome our 3 speakers, as they are Joachim Klink, Head of Autonomous Driving and Integrated Mobility at T-Systems. Hello, Mr. Klink. Kurt Eckert, Senior Systems Engineer, Engineering Advanced Development at Robert Bosch. Welcome, Mr. Eckert.
Hello.
And last but not least, Dominik Schnieders, Head of Edge Computing Cloud XR at Deutsche Telekom AG. Welcome, Mr. Schnieders.
Hello.
And let's start directly with our first speaker. We hear Joachim Klink on use cases and requirements for safe teleoperations. Mr. Klink, what is the contribution of T-Systems to teleoperated driving?
Thanks for the introduction, Alex. And hello, everyone. Thanks for your interest. The contribution of T-Systems within the Deutsche Telekom group is what we naturally do already for 25 million cars. We develop and operate connected vehicle backends with, meanwhile, 200 different connected services. And Teleoperation is just one more service potentially in the future. So everything outside the car, of course, including or embedding a specified or specific teleoperations partner, that is our potential scope. And we do consulting, we do, of course, all the technology integration. And I'm really happy to share a couple of thoughts and also a lot of insights together with my colleagues. So let's start first with a question I'm very often asked. Is direct teledriving possible? And we have 5 different scenarios here. I will give you the answer shortly. Is it possible, for example, on a feeder road, which might be private ground or is usually a little bit less complex than the inner city? We have these kind of low speed areas in Germany called Zone 30, the inner city, or imagine a narrow road with only maybe 5 or 10 centimeters on the side of your vehicle, a parking garage. And so this is the answer I would give. On a feeder road, on a parking garage, we have the capabilities and the possibility to really directly drive a car from remote, for sure. In the inner city, I would say this is a no-go area, at least when it comes to more European type of cities or San Francisco. So where you have a lot of traffic, density, multiple lanes, crossings, bike drivers and stuff. So that's a very complex driving scenario, and I would not recommend to do this teleoperated. These other 2 examples, we currently definitely have legal issues. It's not allowed, to my knowledge, at least not in Germany and most countries I know. But technically it's possible, and I will show you how and why in the next couple of slides. So I'm using a system model of a German handbook for driving assistance systems, so kind of a gold standard, if you will, for at least the German engineers. This is modeling the driving task and all the elements you need to perform driving on public roads. So you have the driving tasks, which is also, of course, dependent on certain surrounding or environmental conditions. You have a driver with certain characteristics, and you have the receptors also first of all from a driver, but also could be also from the vehicle to provide a perception of the situation. And then, of course, do all the tasks that you need to do when you want to drive a car, accelerating, braking, and control of the steering wheel, stuff like that. which will be transmitted to the vehicle, typically normally or inside the vehicle, but let's look at what will change when we do this from remote. Let's think about a really teleoperated driving situation. And the main things what will change is the whole perception thing, right? You have you cannot directly see the road. You see it through a screen or whatever the HMI is, also glasses, and you use the built-in sensors in the vehicle. So there we definitely have a disadvantage because the resolution is not as good. You don't have this haptic or tactile or kinesthetic feeling and perception. So definitely you have some disadvantage as a teleoperator driver. We will see from Eckert later, we also have some potential advantages like a LiDAR, which could be put on a screen to make it better. You can see more than with your human eye. But first of all, there is a couple of disadvantages. And then we have a big disadvantage, which is the transmission of these signals to the driver for the perception, but also then for the steering command back to the vehicle. That's definitely an issue because it's less available or reliable than, of course, the built-in technology in the car, right? We have a mobile network in between. We have this distance, physical distance, and that's the downside. We will look at this more in detail in the next few slides. On the other side, we have a couple of advantages. Especially the driver, we can select the driver. Professional drivers could be better trained, better skilled. We can select from much higher standards than you would do for the normal driving license. We could select from a personality segment, which is calm, which is very professional. So you don't have this, I'm angry, I'm driving a car, and these kind of things. Yeah. Also from an age, we could exclude the very young drivers, which cause a lot of accident, also the very old drivers, which are also not as good in the reaction time. So there we have some possibilities to increase the level of safety and skill. And I would also say we can do a lot on the attentiveness, or on the other side, distraction side of driving, because we can make sure these drivers are really focused and concentrated on the driving task and don't or eat, phone, type, or whatever things we see sometimes in traffic. And let's look on some more details. First of all, we talked about the transmission of a signal. Here is a glass-to-glass latency from the sensor to the screen, if you will. And this typically has roughly around a tenth of a second, 100 milliseconds plus minus. That's, of course, that adds to the whole reaction timeline. And then back to the car, the control signal is a little bit less because it's only very small packets, so the latency is even less. So that is to be added to the original timeline. But if you look at the whole timeline, the reaction time itself is roughly 1 second, and to execute the commands is another 200 milliseconds roughly. And if you look at these numbers, this time could be even worse, right? For example, surprising situations, it goes up another half second. Distraction adds between 100 and 400 milliseconds. Low light situations adds traffic density. So all in all, at least in my opinion, this 100 milliseconds and this one is not the big thing in this whole timeline. We definitely have bigger buckets which make driving a complex and also challenging situation. So latency itself is not the problem. The variation of latency, we have effects, and we will see this later in Dominik's presentation, that the latency can change dramatically or significantly, And that is a big challenge to drive from remote, to directly drive from remote. Let's look at driver distraction, or the opposite, attentiveness. And there you see some situations which we all see probably daily, and you sometimes probably do it yourself. But if you look at the numbers, things like grabbing an object in the car is multiplying the probability for an accident by the factor of 9, and that's a big number. And we nav use, right? You try to configure something on your nav. You have an insect flying around you, or people read and write during whilst driving. So these are things which add a lot of risk to the driving task, and we can avoid these situations with a professional teledriver. So that's so in all in the total equation also to be reflected, I would say. So if you look at it from that angle, we have disadvantages. Of course, we add some latency here. On the other side, because we have a very focused and professionally trained and very skilled driver, we could even take out latency from the overall timeline and become even better. And on the other side, we have some risk of network outages or data loss or whatever, slowing down or whatever, reduced resolution. On the other side, we can avoid all these situations which we experience every day, where people are really distracted and cause accidents. So to me, we can be, I think in certain situations, and in definitely more situations than we currently think, we can directly teledrive a vehicle from remote. And these are the situation I look at where teleoperations makes really sense. Not every time direct control, but for example, here the remote last mile delivery of rental cars, of shared cars, in a very not in the inner city, but in a more remote area where the streets are very wide, stuff like that. I could imagine this could work. Also, of course, on private ground or on these kind of whatever trailer yards or a big parking lot, where you can control the network quality, this can also work. Of course, whenever we increase the safety of the driver, we take him out of a dangerous situation, and we don't have a lot of other cars and traffic participants around. That also makes a lot of sense. And ports or even airports, when operating multiple vehicles at the same time, this would not be a direct driving situation. Again, that makes a lot of sense. Whenever we have to manage unexpected or complex to handle situations, we can kind of complement or replace the automated driving function. And even by design, for example, in this case, a sweeper or a snow remover on an airport, a very simple to automate driving task, straightforward, 180 degrees straightforward, not a lot of things around, very easy. But you have to get the vehicle to the area of operation, and that's a more complex driving test. But this is only needed maybe 10 minutes a day. So this could be an interesting application area. And then automated valet parking could be also complemented by teleoperated valet parking, not only in the fallback situation, but even by design when parking garages do not have the infrastructure which is needed for automated valet parking. With that said, I'm happy to hand over or give back to the studio, and I'm interested in the following presentations. Thank you.
Thanks a lot, Joa, for these valuable informations, and thank you very much. Our next speaker is Kurt Eckert on 5G connected and automated driving use cases, technologies, and trials in cross-border environments. Kurt, how does 5G bring us forward in automated driving beyond level 2+?
Well, of course, we always try to make the car as independent as possible, letting that car overcome as many situations as we can in an autonomous way. But there are situations that we might not be able to overcome completely, and in that dimension, we have, for example, the support of infrastructure, which can help in the autonomous driving, and by far, I would say, most complex and challenging use case is what Joachim just mentioned before, the teleoperation, and so in general, teleoperation, it's quite clear how it works. You have a certain situation like the crash here, which the autonomous driving or car cannot cross. And for that, it would then question or check the teleoperation center, hand over the control to the teleoperator, which then, however, we will see it a bit later, is able to help the autonomous vehicle to overcome this critical situation. And at the end, of course, when the critical part is done, the teleoperator will hand over back the control to the car, and the car is then going on in an autonomous way as before. We were looking at teleoperation quite deeply in a European Union funded project called 5G Croco. And in that project, we had two kind of corner cases for teleoperation. One is a real direct control, so having a human driver sitting in front of a steering wheel, having pedals that allow to steer and control the car in a direct way with a communication via cellular networks. And another maybe less challenging use case for the communication side is an indirect control use case that we also were investigating. And in that case, you still have the video. So in uplink, you still have quite challenging requirements for the communication side, but the control itself is done by providing to the car what we call trajectory. That means points with a position, geographical way, and also timestamps. And that information is then handed over to the car, and the car is driving along those trajectories, and by that is able to overcome as well those kind of critical situations. We now have two short videos that on one hand show the general way things are working, and on the other hand have some examples of the tests that we made in this before mentioned project. It's tests that were done at cross-border areas. So we also wanted to know what's happening when we have to move from one operator, so cellular operator, to another one. Does that decrease the quality in a way that we cannot go on? It was an important issue, and we wanted to find out how far we can tweak the communication systems that they even help us in teleoperating when it comes to a handover. So now I would ask to start the first video. So I think it's starting now. It's quite clear. The vehicle stops in front of the critical situation, hands over the control to the teleoperator. The teleoperator, in that case, is really using its steering wheels to steer the car, maybe besides or on the pavement, to be able to overcome that situation. The next video is showing what we really implemented and how that was working in the project. Yeah, as you can see, there's the operator sitting in front of videos. We have a kind of surround view because we also need to look at the side and also back. We have pedals and as said, the steering wheel that directly then interacts with the car. And we will see the video, the situation that the teleoperator can see when he's driving. It's more or less like sitting in a car. With some additional things. And here we have a view inside of the car. Of course, we need to have a safety driver in our systems because it's all prototypes and we are not allowed to let them drive on roads without a safety part or people that can interact with the car whenever it's necessary from a safety point of view. And then we can go on to the next use case. The already mentioned indirect control use case. In that case, it's more or less the same, but the difference is that the car just gets this trajectory and then uses its own driving capabilities to drive along this trajectory. It's of course monitored by the teleoperator, and the teleoperator can at any time interact and for example, put the car to a stop when something should happen that was not, or that is happening on a very short time frame. And the next video then will show was really looking at the teleoperator side. In that case, we did not only have the video, which is on the left side, we also had a LiDAR representation of the area. That is sometimes, it's looking a bit maybe strange, but a really experienced operator can get a lot of information out of that kind of representation of the environment, like three-dimensional things and other things. So now the teleoperator, he has provided the trajectory. The car is checking that trajectory and sending back the one that it's really driving, because the car might drive a bit different than the teleoperator is telling. Because of limitations that you have in your vehicle, you cannot make very sharp turns or things like that. The teleoperator would then accept this real trajectory, because there could be cases where it doesn't fit, and then it would need to be corrected. But in that case, it was fitting. The teleoperator was putting on accept, and then the car is starting to drive, but still sending its video information back in order to have the chance to control what's happening. And when at that time something unforeseeable would happen, there would always be a chance to have a safe stop from the teleoperator side. Okay, car is getting to its final position, and yeah, so from a car point of view, it was more or less looking the same. We had the safety driver taking over whenever it's necessary, but at the end we were able to have these both use cases and to show them even in well, 5G scenarios where we have handovers and things like that. Okay, next slide is getting or showing, looking a bit at the challenges that we see at different parts in our overall system. One thing is, of course, the vehicle, where we have fixed capacities. We don't have endless memory. We don't have big computing power in our systems. We have control units that have limitations. We need guarantees, because whenever we do actuation in the car, it might cause accidents and severe accidents. And for that, we need guarantees for what we are doing with respect to the data that we get and also with respect to the computation, for example. We need reliability, of course. It has to work anytime. We have different tasks in the car that are running in parallel, and for that we need to put priorities to some of the tasks and need to be able to distinguish between the important ones at a certain point in time and the ones that are that maybe can be delayed, things like that. And we have, of course, security and safety barriers in our systems, which means that part of the system is not safety relevant, but another one is, and we have to clearly distinguish between these different parts of the system, and also kind of have firewalls in between and things like that. Then on the communication side, we have, of course, if we were asked to put a wish, we would say we need fixed assignments of capacity and latencies, which are really very low. And of course, in our case, high data rates, especially in uplink, which is a challenging thing as well in actual or current 5G networks. But we of course know that this is all just can be kept up to a certain extent, and we have to overcome also situations where the communication side is not able to provide us perfect communication. On the back end, of course, we have scalability. We don't only want to control just one car. We need to be able to control several ones, and for that, systems need to be scalable. We might need redundancy because at least on the cloud side, on the part that we are putting on the teleoperator side, we more or less have to apply the same or nearly the same safety measures. And for that, we might need redundancy in the system in order to be sure that things are always available. We have to cope with big data, like the mentioned LiDAR clouds, which are really big. And we also think about neural networks that could help us to overcome critical situations. From the features that we need from our telecom providers, of course, high data rate is something that we need for teleoperation. In uplink, in downlink, it's not really critical. In downlink, it's just control commands, which are very small packets, and we don't need data rate in downlink, but we need really severe data rate in uplink. In our use case that we had in the trials that we made, we were using 7 HD cameras that were in parallel transferring their images, and we stitched that then to an overall view for the teleoperator, and by that you can see that it's really challenging here. We need high reliability, of course. We need low latency up to a certain extent, as Mr. Klink was mentioning before. And we also think about using quality of service prediction, and that goes together with functional safety. When we would know in advance that the communication system has a degradation, we could take that into account in our safety considerations in the system by, for example, reducing the speed that we are driving, or already preparing our system for hard brakes and things like that. And by that, quality of service can really help us to overcome critical safety areas. From a safety point of view, we are not expecting safety inside of the telecommunication networks. What we would do is, and how we think about the concepts is, we control and monitor the communication. We have to know in a safe way whenever the system is degrading from a communication point of view. But then we need to be sure to get into a safe state in our systems on the vehicle its own, because otherwise it would put high reliability and even safety requirements into the telecommunication networks, and that is something that is, even from an economic point of view, not reasonable from our point of view. But we have concepts that allow us to do so. We, however, need still a high reliability from the communication side, because that is something that we really need in order to make our products at the end real acceptable by the customers. We cannot afford that a system is stopping every 5 minutes because of communication is bad. That is something we will not be able to. But we don't need 99.99999 reliability. And by that, I'm finished with my part and hand over back to Mr. Heintzel.
Yeah, thanks a lot for this very interesting presentation. And ladies and gentlemen, last but not least, this webinar will be rounded off by Dominik Schnieders, who will inform us on managed latency in the context of teleoperated driving. Dominik, how does edge computing help us to map 5G?
Yeah, thanks, Alexander. We will talk about edge computing and 5G in combination in order to get a stable latency, managed latency in the network for teleoperated driving. So let me start with a view here. let's go on. Let me start with a short video that we did in order to explain the experience that you get from managed latency. We took as an example cloud gaming, what you already see here in the picture, and we compared on two sides the situation with 5G and without managed latency on the left-hand side compared to a 5G situation with a managed latency. It's that boat race that we did with cloud gaming, and underneath you can see an experience later in the video how the change of the latency, the jitter or the variation of the latency influences the picture that you then recognize. And that's the same for teleoperated driving. If you want to do the transfer to that, it's exactly the same situation that you transfer a video image in that way from the camera to the remote driver. And here again, this video shouldn't stop. So let's start the video. If you could be so nice to do that centrally. Excellent, thanks a lot. So what you saw in the video, and I hope you could recognize that that there's a big difference in the experience in the way that the video was transmitted, and that depended a lot on the latency. You already saw the keyword L4S. That's one of the technologies that we will look into in the upcoming session, and it's a way to stabilize and manage the latency. And I just wanted to emphasize that this comparison was totally fair. It was on a 5G system that we did in the lab together with Ericsson, and it had exactly the same radio conditions on both sides. So it was a really fair comparison between the two scenarios, and it shows the advantages if you have a stable latency. And it's important that this is not only working for cloud gaming, but a whole lot of different kind of applications that I would just like to point out. It's important because if you would build a network feature just for one application, that could be, well, economically a little bit difficult. So you can use it for cloud gaming with the offloading of the game engine and the rendering. You can use it for multiplayer games, which is obvious. It's interesting to see that augmented reality streaming and virtual reality streaming also are really helpful, because you can offload part of the computation, can make the device, for example, glasses, simpler, cheaper with the offloading. Complex calculations, like you see on a occlusion calculation, can be done on the edge. And again, it's necessary to have a stable latency. Video conferencing is something we experience, unfortunately, every day due to COVID, that sometimes the image freezes. And you could overcome that if you have a stable latency or a mechanism to get the packets constantly flowing through the network. And that's exactly our part of the technology that we introduce. On the automotive side, you can think about offloading parts of the calculation. And the same, it's interesting for a vehicle-to-X communication. And of course, the teleoperated driving part. And we also did a lot of prototypes on the drone side, on the AGV side, for offloading either video camera or LiDAR to an edge cloud, for example, do object detection in the cloud and bring back that information to the device. But today it's about teleoperated driving. So let's look at the effect of that managing latency technology for teleoperated driving. First, we did around 50, 60 prototypes with partners in all of that areas to understand what really the requirements are. And we learned that the stability of the latency is the most important aspect for all of these applications. And Joachim mentioned that before in his presentation, stability is essential for teleoperated driving. It's also clear if you have sometimes a high jitter, if then the packets, your video frames from the camera don't get through the network, the remote driver can't see it. So we need to stabilize the latency. That's essential. And we also call that sometimes upper bounded latency, and to try to do that indication in that picture here. Second one is the average latency. That's like an average reaction time of the system. And we want to have that as low as possible. But we also learned it's not always necessary to have the lowest average latency. But a lot of these applications can do in a right frame and a right ballpark of the average latency. So we bring that down also by reducing variations. And there's a lot of 5G features also to improve the latency overall and get a lower average latency. So that's, let's say, the second place, what we need to do. And the third one is the bit rate. And here's really the interesting part that we learned from our prototypes with the partners over the last years. All of these applications are able to do rate adaptation. They do it actually today, but they do it from outside without knowledge directly from the network. And they can do that for video applications. Let's take teleoperated driving again, by changing either the frame rate, which has an impact on the latency. So we should look at that really closely, but especially encoding, compression, and of course, resolution. Now, they can adapt, but of course, we always want to give them the best, highest bitrate that's possible in that situation. So actually, the quality, of course, is better when we have the highest possible bitrate. And very often this is possible in the network. But there are conditions where it's really difficult to still provide that high bit rates in combination with a low and stable latency. And that's exactly, let's say, the point where we step in with that managed latency via alpha-S technology. First, to understand where does the latency come from, let's have a short look at that picture. It describes the network side with the air interface here, with the transport and aggregation between base station and our core network, and then from the core network over the IP backbone into the internet. In order to improve, we do edge computing. We have rolled out edge computing in our network here in Germany on 5 edge data center, and that reduces the latency that you have between, let's say, the cloud or the core network and the internet, going over a higher distance, and of course, additionally risks for jitter due to peering. So the closer we are, the better it is. Is it enough? Probably not, because if you look at here the picture, you can illustratively see that the air interface causes most of the jitter and the most variation. In the core network and aggregation core network, it's also possible to optimize, but there it's more load independent, more stable, because we can use fiber, but the air interface is the wireless one, the more demanding one. Now, if you have a closer look at that air interface, we see that this variation is the part that we need to take care of. The reason for variation is manifolded. It can be in some situations that the cell is more loaded because actually the users can be in a cell anywhere. They can have an event, and due to that, there's just a more loaded cell that can happen at any time. Sometimes you're at the cell edge, and then your signal conditions are worse, and that influences latency and jitter. Of course, also indoor. If you have sometimes attenuation due to changing radio conditions, the radio wave propagation, that can again change the quality there and lead to latency and jitter and interference. And mobility makes it even a little bit more complicated. Of course, there's a lot of methods to deal with mobility, but it makes it more difficult than a static user. And there are ways to influence the latency. Very important one is quality of service with prioritization. We do this for voice over LTE, for example, or voice over new radio. There's resource reservation, and of course 5G brings a lot of different features to improve the latency, smaller TTIs, low HARC retransmission time, just to name a few of them. But we are also facing a situation where physically it's not easy due to the physics to optimize, let's say, all of these three aspects, that triangle that you see here at the same time. So just imagine you want to have a high bit rate. It's best if there's only one user in the cell, he gets all the spectrum, he's just besides the base station to have the best signal quality, and he will get the best bit rate. But if you have a high number of users in that cell, they share the spectrum. It's just a shared network, and it's wireless, of course. So if some of them are more at the cell edge, it's getting more difficult to give them the same bit rate, or it's not possible. So they share that that capacity. And if you want to improve the quality, which we want to do for low latency, you need to use more of that spectrum in order really to achieve that stable and low latency. So it's understandable that with classical ways, it's not so easy to optimize all three parts at the same time. It's always a trade-off. And that's, for example, the reason why voice over LTE is easier with prioritization, because the bitrate is very low. So it's scalable, bitrate is low. We can better prioritize without harming other users. So what is the solution? We need to provide a low and stable latency. We need to be super efficient on resources in order to be scalable. There can be more teleoperated drivings, cars, more other users that need low latency. It needs to be fair in terms of resources. That's also important, very important from regulation side. And it needs to work in all kind of frequency bands. So it's really working countrywide in a good way. The concept that I would like to present to you, we call it managed latency, focuses on that aspect that we learned, that stability of the latency is the most important aspect. So as you saw in the video, we want to avoid that here, this principle with the Mona Lisa image, that there's some frames not being fluently transmitted to the network because due to congestions, and you don't see that picture. We want to achieve with that managed latency that the video frames, for example, from teleoperated driving, are constantly flowing. And we achieve that by actually bringing very simple two aspects together. First of all, you need prioritization, as you also know from voice over LTE, which is prioritized. That's causing that the packets are picked immediately. In order to be scalable, fair, and good, it's important to have a feedback loop, a coupling between network and application. And you can imagine that a little bit like that analogy down here with the central heating and the radiator. On the one hand side, you have a sensor with the radiator and you have the central heating, and there's a feedback loop in order to get the best temperature. And that's the same, and which we will see now, what we achieve with managed latency in the RAN. So here, a short close-up of a base station, just with some important components for us, the queues of the different connection between server side and the smartphones or the device side. There's a scheduler that picks the packets out of the queues, and then there's the transmission side with the radio part. And actually, you see that there's a queuing, and that queuing, that's the part that that we learned before. This queuing is very much bringing that aspect into it, that we have a latency there. So actually what we do here is we do prioritization of the packets, it runs through, and we have a fast feedback loop in order to rate adaptation. So that's a basic principle about it. How is the implementation that we did with Ericsson together? We based it on a standard called L4S. It stands for low latency, low loss, scalable throughput. Actually, we have that sensor in the network here that sets the ECN bits accordingly to the congestion state, so the queuing time, which is the latency. You get a direct feedback out of the network about the latency that you just experience. If the queue is rising, the latency starts, a jitter is appearing. And on the UE side, on the application side, you read out that ECN bits out of the IP header, you transmit that back to the server, and you do rate adaptation. So that's basically the idea behind it, and it's based on a standard which is essential because it needs to be scalable for all operators to work worldwide. So that's why we based it on an IETF standardization. And it's actually what you saw in the video. Shortly looking at some measurement results, we're working together with Ericsson for over 2 years on that. We tested it in all kind of network conditions, cell edge, cell center, mobility, in a field test with driving tests, as well as with very bursty background traffic. And you can see here again, like in the video, the orange is the latency curve, that sometimes you have that latency spikes, and we can stabilize the latency. So let's conclude that by looking at teleoperated driving in combination with that managed latency with L4S. First, we learned and we know that there's a video feed from multiple cameras on the uplink, which has a high bit rate or requires a high bit rate usually. We have that control commands, maybe including audio on the downlink. And we see and learned in a lot of discussions and looking into it that stability of latency is really essential for teleoperated driving. What is also possible is to do rate adaptation if it's required. So let me repeat that. Usually you will have a high bitrate, but sometimes application and network needs to work together in order to stabilize that latency, and therefore rate adaptation in that situation is required just to avoid that packets don't get through and the video for the teleoperator is freezing. And mobile networks, in the nature of it, uplink is more difficult than downlink. And for that reason, we need to be super efficient, which again is very helpful if you do that prioritization with that feedback loop together. So let me summarize. Managed latency with L4S, it provides low jitter. It is super efficient in terms of resources, and it also works very well in mobile scenarios. And in the end, we can think about combining that also with a mechanism to take care that we at least have a minimum bit rate, which can be still very efficient. So thank you very much. And I will give back to Andreas.
Okay, thanks a lot for this deep dive. Gentlemen, thank you for your presentations. During your speeches, I had a couple of questions coming up in my head, and I tried to reduce them for one question each. If you don't mind, I would ask you those three questions I picked out as the most interesting ones. Let's start with Dominik. By how much % or to what value does the bandwidth have to be reduced for AML to work?
Very good question. It is in the way that we always will give a feedback that is related to the network conditions. And principally, there's always a maximum that you can transmit under certain conditions, other users in the cell, where you are in the cell, and we guide you to that approximately maximum, maybe a little bit offset, but as close as possible to the maximum bitrate that you can transmit in that situation. So therefore, you need to reduce it, but you will be guided from the network to the nearly optimal point of that bitrate transmission.
Thanks. Kurt, how do you assess the possibility of OEM independent teleoperation service providers playing a role? He doesn't listen. Okay, he cannot hear us. So
I was unmuted by the.
Okay, sorry. Could you hear me?
Yes, of course. Okay. But you can repeat maybe to be sure that it's.
How do you assess the possibility of OEM independent teleoperations service providers playing a role?
Well, I think if we would really get into systems where we have independent operators of the control centers, that would add another, I would even say, dimension with respect to safety. In principle, it could be, of course, possible, but it will impose a lot of additional requirements. We have to trust each other. We have to standardize things in a more rigid way. We have to have organizations, who's taking over, and these kind of things. So from my point of view, it will be a long time where the OEM will have the car and also the control center in its hand.
Thanks. And last question, Joa, do you think that in the near future vehicles will drive remotely through German cities as the startup Way recently outlined?
Actually, no. I hope I got the message across. I'm very confident in direct driving, direct controlling a car from remote, in certain conditions and areas. But the report or the press release was related to Berlin, the inner city of Berlin, with a super complex traffic situation. I mean, you have bicycles driving like hell around you and these kind of things. I'm even challenged as a normal driver, and I'm a good driver. At least I consider myself being one. and I would not do this from remote. The responsibilities and all we heard today are adding a lot more risk to this, and this is definitely an area where the built-in systems of a car have to fail or would stop the car almost all the time because you have so many traffic participants around you. So this exact described situation, I would not do this. But as said, in many other areas on public, even on public roads, I fully trust this is potentially possible.
Good answer, thanks. Ladies and gentlemen, we have arrived at the end of this webinar. If you have any questions, it's not just me having questions, of course, they can be asked via email after the event. The speakers will certainly be happy to answer them. Many thanks to you, gentlemen, again for your in-depth presentations. And of course, our thanks also go to you, our participants. This webinar was recorded and will be archived on the website. An email with a link will be sent to everyone who registered for this event. It would be nice if you could also answer the feedback questions that you see right after. Ladies and gentlemen, thank you again. Stay safe and goodbye.
Bye.
Thank you. Bye-bye.